Thank you all for coming in person and on Zoom. I really appreciate it. All right, so what I will be telling you about today is some work. Sorry, one second, let me get my timer going. There we go. Work that I have done that is leading up to eventual work on constraining non-standard neutrino interactions, which we're calling NSI, in IceCube Deep Core. Okay, starting off with the standard model, which I'm sure most of you all are familiar with, maybe not everyone on Zoom. This is the standard model of particle physics. It describes the elementary particles that we believe to exist. Neutrinos are three of these. They are fundamental particles with no electric charge, no color charge, half-integer spin, and very small masses that we have yet to totally pin down, but they're on the order of eV. As far as we know, they interact only with the weak force, so the W plus and minus bosons and the Z0 bosons or boson and gravity. But the idea of non-standard interactions is, what if there are more things that neutrinos could interact with? What would that look like in experiments? There are a lot of reasons neutrinos are really cool. One is they can be described by two bases, which are not the same basis. There are flavor states and mass states. The flavor states are the eigenstates of the weak interaction. So these are the neutrinos that interact with W and Z. These are nu E, nu mu, and nu tau, and they're named after the charged lepton that they couple with in that interaction. Then there's also the mass states, which are the eigenstates of the Hamiltonian. These are nu1, nu2, and nu3, and they have masses that we have yet to totally pin down, m1, m2, and m3. And these are what we say neutrinos travel as, because they are eigenstates of the Hamiltonian. The bases, as I said, are not the same. They relate through the PMNS matrix, which is a mixing matrix. It contains the mixing angles θ12, θ13, θ23. And you can see those laid out as Euler angles in this pretty cool illustration here that I pulled from somewhere. So we're seeing the mass basis in orange and the flavor basis in blue, and they are rotated with respect to each other with these mixing angles. Then there's also a phase factor, delta Cp. This could possibly violate charge parity symmetry if it exists. And that's also in the PMNS matrix. As I said, neutrinos travel as their mass states and they interact as their flavor states. And because of that mixing, that leads to the probability that a neutrino is detected in a given flavor state oscillating over the course of that neutrino's flight. And that's what we mean by neutrino oscillations. We can look at how that works in a bit of a hand-wavy way in this two-flavor toy model. So this is the idea that we have two flavors of neutrinos and also two masses. So the way that this works is we're looking at the probability for a neutrino that starts as a flavor alpha to be detected in flavor beta. And we have the singular mixing angle in this toy model here as theta and the mass squared splitting as delta m squared. The way the delta works with the squared is we square the m's and then we subtract. So this delta m squared could be negative. And this is the difference in those two masses. And then we have two independent variables here, which we sometimes kind of consider as one combined independent variable, L over E. L is the baseline or path length, or the distance that the neutrino travels before it is detected, and E is the energy of the neutrino. So here we are plotting out oscillation probabilities for an initial muon neutrino in the full three flavor picture. It starts, as we can see, as a muon neutrino, the blue color, and it has 0% chance of being detected as a tau neutrino or an electron neutrino. But as the neutrino travels, we're looking at length over energy as our combined independent variable. We can see that that probability changes. And that is what we mean by oscillation. Okay, atmospheric oscillations analyses. So this is one kind of analysis that we can do in order to get at these mixing parameters, these oscillation parameters, or I'll just call them the physics parameters in general. The idea is we want to reconstruct the energy, direction, and flavor of neutrinos from detector data. And here we'll use atmospheric neutrinos because we know their baselines through their directions. By direction, I mean the direction that a neutrino comes through a detector. So we can trace that direction back through the Earth, and when it hits the atmosphere, we know that's how far the neutrino traveled, and that gives us the baseline and L in the oscillations equation. And then we also have atmospheric neutrino flux measurements, and that gives us alpha, or some sense of alpha, which is our initial composition of flavor states of neutrinos. And so through that, we can use the oscillations equation to constrain our oscillation parameters. And the ones that are most relevant for atmospheric measurements are theta 2,3 and delta m squared 3,2. And I've just written the oscillations equation here again. To make it a little more visual, this is a kind of plot that I'll be showing a lot during this presentation. This is an oscillogram. And the axes are all going to be the same whenever I show this plot. So on the x-axis, we have the energy. We're on a log axis. Here we have cosine zenith. Zenith is the angle. And so you can think of this as being related to that L, that length. And then on the color axis, we have probability. So here we're looking at an initial muon neutrino, the probability that it will be detected as a tau neutrino in a charged current interaction. Charged current is W boson interaction. And you can see this pattern here. We can call this the oscillations pattern. And this is what we are trying to resolve. If you look at the two-flavor oscillations equation, which I'll claim behaves enough like the three-flavor that we can hand wave through it, you can see that the mixing angle appears as this kind of scaling factor when we consider L over E our independent variable. And the mass squared splitting appears as kind of a frequency in this parameter space. So the idea is that the mixing angle controls the height of these valleys and peaks, and the mass squared splitting controls the width of them. So we can make an oscillogram or an oscillations histogram and fit the oscillations histogram to get out our physics parameters. And then because we have two physics parameters, we can plot contours. So what these are is we are drawing shapes in our physics parameter space that we are some percent certain the true value lies within, or we are some percent confident that the true value lies within. So you can see a number of experiments have drawn these contours in physics parameter space. We got NOVA, we got 2D-K, we got Super K. And then here in red, this is a projected contour, so a sensitivity from 9.3 years of IceCube data. Is that a quick question on Zoom, or is that somebody accidentally unmuting? Okay.
So can I ask you?
Sure.
See the question. So your equation there was 1.27.
That is a factor to make the units work. It has so it comes along with units to make the argument of the sign be unitless, and it also allows you to plug in these particular units. So EV squared, kilometers, and GeV. And so the 1.27 makes the math work out. So those are the units you plug in, and then you also get a unitless thing inside the sign. All right, so now talking about matter effects and NSI. So the idea here is that neutrinos scatter off of matter in their path. So all we've talked about so far is vacuum oscillations, but if neutrinos are going through matter, they will scatter off of that. And that scattering looks like a change in that neutrino's oscillation parameters. And to hand wave illustrate that here, I've got a plot. We've got vacuum oscillations in blue. We're saying this is at a neutrino at some fixed energy, so distance is our x-axis here. But say the neutrino is actually going through some density of matter. And here we've got two models of that. We got this very fine model in light gray. Then we have this castle wall model in black. And here's the oscillation, this is the survival probability. So the probability neutrino stays or is detected in the same state that it is produced. We can see that that probability looks a lot different than the vacuum oscillations probability. So we can model that change as a change in the oscillation parameters. So that's matter effects. We can consider that an effect on oscillations, and then an effect on matter effects is NSI, non-standard neutrino interactions. There are a number of beyond the standard model hypotheses that are created that explain why neutrinos have mass, which itself is a beyond the standard model property. And many of those predict an additional heavy mediator boson, so something else that would interact with neutrinos. And the idea is if neutrinos are going through the Earth, say, or matter, then they're interacting through with that matter, maybe through this other boson as well. And so that's also going to impact matter effects and oscillations. Scott?
So can I ask a quick question on the speaker? So is the
Sure.
so that's calculating the matter effect within the standard model, or?
Well, oscillations themselves are outside of the standard model.
Standard oscillation.
Yeah, these are the standard oscillations, so with no matter effects.
Mhm.
Whereas in blue, in red is with these matter effects of the Earth injected, kind of, if that makes sense. Okay.
Doesn't include non-standard E interactions, right?
Yes, yes, yes. So there's three things to consider here, right? There's standard oscillations. There are matter effects, and then there's NSI, each of which is a like correction on the last. So it's kind of this tiered structure. Okay, so interactions with any other boson is considered non-standard neutrino interaction. So it's this very broad category. And as I said, that'll impact matter effects. We want to evaluate NSI effects because, as I said, that informs beyond the standard model hypotheses. And if we've got something else fundamentally going on with neutrinos, then that'll also impact our normal measurements of oscillation parameters. So these are very relevant for neutrino oscillations experiments. How do we search for NSI? IceCube and a number of other experiments and a number of other searches for NSI try to use this most general model possible. The idea is we have 6 effective coupling parameters. And what you want to be looking at here is this matrix here. So we are looking at the matter potential for neutrinos as they're traveling through matter. These epsilons are perturbations on this matrix. The basis of this matrix is the neutrino flavor basis. So we have what is affecting electron neutrinos in the first column, muon neutrinos in the second, tau neutrinos in the third. And then the rows are what neutrino comes out. So electron neutrinos in the first row, muon neutrinos in the second, tau neutrinos in the third. If there's no NSI effects, these are all 0. If there are NSI effects, some of them could be not non-zero. We have this 1 here because this is the matter effects. So we're talking about, see, we're in the electron neutrino column. So we're talking about when electron neutrinos scatter off of electrons. So that's the matter effect. So that would still be present even if there were no NSI. All these parameters impact the oscillogram, so we can extract them from fits. And I've got a little animation, a manual animation to show that. So here we're looking at the probability for an initial muon neutrino to be detected in a charged current interaction as a nu tau. Here we're looking at standard oscillations. Here I've injected epsilon nu tau to 0.02. You can see it kind of shimmies around. And it shimmies more towards these lower angles. That's more towards the core. So there's more matter there, and it's more being affected. In fact, this kind of almost looks like a discontinuity right here is the Earth's core. So that's fun. And then here's the difference between these two, NSI minus standard. So you can see this is something we could get at by making these oscillation histograms. Let's talk about IceCube. So IceCube's basic design. It is a cubic kilometer Cherenkov detector at the South Pole. This is a whole layer of, or the whole surface of the ice is right here. And then 1 kilometer down, there's this cubic kilometer detector. It's an array of 5,160 digital optical modules in ice. These are DOMs, and they look like this. You can see they're pretty much PMTs with glass pressure housing and electronics. They're connected on cables called strings, and they send their data up through their cables, and they're also suspended on the cables. There are a few other pieces of instrumentation, such as IceTop, but I won't discuss those here. IceCube is very cool for a number of reasons, one of which is it has a ton of physics goals. It's got astronomy goals, and it's got particle physics goals. Some of the astronomy goals are identifying the astrophysical sources of high-energy particles and being ready to observe a galactic supernova. And some of the particle physics goals are constraining our physics parameters I mentioned, sine squared theta 23 and delta m squared 32, and also searching for beyond the standard model physics. The detection physics is that a neutrino interacts with a nucleus in the ice, and that creates a charged lepton secondary, so an electron, muon, or tau. That secondary is, if it is traveling faster than light in the medium of ice, it emits Cherenkov light, and that is in a cone that follows its trajectory. The Cherenkov light propagates through the clear ice and is detected by the PMTs and the DOMs, and the DOMs report the charge and time information through their cables up to the IceCube lab on the surface, which broadcasts out via satellite to Madison. Here is a video. So in red, this is the neutrino. In yellow, this is a nucleus inside the ice. And we're going to see a secondary come off with this blue cone of Cherenkov light and hit the DOMs. The Eiffel Tower is also here. And there's our data. That's a great question. Yeah. Yeah. I love the systematic in IceCube. It's where's the Eiffel Tower? All right, so that is how IceCube detection works. There's also deep core. This is a sub-detector. in IceCube. It's a more densely instrumented array of DOMs over 8 of the central strings. It's these red strings. We're looking at this top view here. Here's a side view. You can see it's more dense. The idea is the high density allows for energy and direction reconstruction for smaller energy events because the light is deposited over a smaller length. And for IceCube, that's GeV scale events. And you can see that is relevant for our oscillation histograms because we're looking down here at the single or double digit GeVs to make our plots. So this is relevant for oscillations and NSI analyses. All right, previous work that is involved with my work and leading up to my work is FLERCNN. This is the fast, low energy reconstruction used in convolutional neural networks. It is a project, it's a reconstruction and oscillations analysis project led by MSU alum Jesse McAuliffe. The reconstruction part is it uses these convolutional neural networks, CNNs, to map DOM data to neutrino energy and direction. And also the what kind of neutrino it is, the PID. And remember, these are the relevant things that we want to plot in our oscillations histogram. The reason that a CNN works is that the physics that produces IceCube events, we expect it to be translationally invariant, so it works with this idea of convolution. And also events can be read as images. So image recognition can work to reconstruct events, which is kind of very cool. The oscillations analysis part is we use these reconstructions to fill the oscillation histograms, and then we fit these histograms for our physics parameters, sine squared theta 2,3, delta m squared 3,2. The way that fitting works, first we choose nominal physics and systematic parameters, and we create Monte Carlo simulation, MC, using those parameters as our nominal. And we reconstruct the MC's energy, direction, and topology, by which I mean PID. Or here, let me go into a little tangent here. So we have cascades mixed in tracks. New mu CC events characteristically have tracks in the detector, that is lines of DOM data, whereas most other interactions generally have cascades, which are spheres of DOM data. And so we can use that as a handle to figure out which events are new mu CC. And FLERCNN is doing a new mu disappearance analysis, so it's important to count the number of new mu's, and this binning is the way we do that. So anyway, we use this binning, we call this the analysis binning. So we got energy, direction, and topology. We bin the MC events on that. You can see there's bin counts in tiny font in here. Then we compare these bin counts between the data in the Monte Carlo through a test statistic. The idea of a test statistic is we want to get one number that represents in some meaningful, relevant way the difference between the data and the Monte Carlo event counts in these bins. We call these maps also, by the way, so I might refer to these as maps. And then we want to minimize the test statistics. We want to minimize the difference between the data and the Monte Carlo to make the Monte Carlo match the data. And we use a minimization process and change the physics parameters. And the way that we create new simulation, or the way that we create new Monte Carlo with changed physics parameters, is this process called reweighting, which is, I believe, somewhat unique to the software framework IceCube uses, where instead of generating new simulation, we can calculate what the effect of having different physics parameters is on the bin counts and use the bin counts directly. So it saves some computational time, and then we go through this whole process to minimize.
Apologies for the
Oh.
largely infected all of the neutrino experiments.
This is good to know. I apologize for the mistake. All right, let's talk about my work. So before last summer, I pursued several smaller projects. These introduced me to the collaboration software and led me to NSI through the slightly roundabout path of neural network reconstruction to FLERCNN to oscillations analysis to NSI. Last summer, I worked as part of the FLERCNN team to create, interpret, and present plots during the analysis's unblinding stage. I generated many versions of these same plots along the course of the unblinding. Up next, I'm going to show a few plots. These are at arbitrary points in time, so don't consider these final level, consider these more just for illustration. And also these will not cover the full, this is not an exhaustive description of the entire unblinding procedure. These are just some relevant ones to give you all a sense. All right, this is an Asimov inject recover test. So we have physics parameters on the X and Y. Notice this is a different physics parameter than the one we report, but is the one we fit to, and then we do a conversion. And the idea here is we want to show that the minimizer in the analysis procedure can, in principle, recover the relevant range of physics parameters. So what we do is we reweight pseudodata, so Monte Carlo, to match given combinations of physics parameters. We have this in this grid in analysis or in a physics parameter space that we think should cover the relevant range. And so we reweight pseudodata to inject those physics parameters. Then we perform a fit to the pseudodata and see, does the fit match what we injected, which I think is fairly straightforward. Might be a little hard to see, but there are truth points behind these fit points, which is a good sign. That means they line up. And so in theory, the analysis should be able to recover this range of physics parameters. Here we are looking at bin-wise poles. So by poles, I mean this kind of metric here. It is some scaled version of the difference between the data counts and the fit counts. And we are once again in analysis binning. Green bins have been masked out, which I will explain in a second. So here we are comparing the data and the fit in the analysis bins. So here, if we see a region where the poles, these differences, are very large or clustered in some direction, then we say, oh, that's a region that we are not simulating well. So maybe we should not include that in the analysis. For example, these already masked out green bins are such regions that have already been masked out. This is the ensemble test. The idea here is that we want to show that a fit to the data is typical or not atypical for some given physics parameter hypothesis. So here we are creating pseudodata trials by applying statistical fluctuations to the bins of the best fit point map. So I'm going to go back a few slides to look at a map. So here we're looking at each one of these numbers. We say, what if that is the mean of a Poissonian, resample that Poissonian, and put that as the bin count instead. And so that is giving us for all of these bins, and then for many different trials, so many different maps, say 1,000 of them. And that gives us pseudodata that we say could be consistent with, or is consistent with the same physics parameter hypothesis, but is not exactly the data. And then we perform fits to all of that pseudodata, and we get this expected distribution of test statistics. And here we're using modified chi-squared as the test statistic. So we compare that test statistic distribution with the actual test statistic of the data fit. And if that data test statistic is far to the tail of the expected pseudodata test statistics, that means we have an atypical fit. The test statistic is atypically high. The fit is atypically different than the data, and that would be a cause of concern. We want to go back and modify the analysis.
Okay.
Yes.
So in your previous slide, you were talking about data, right?
Yes.
So I'm just curious, this one is the real experimental data or?
I believe so. Yes. Here are some preliminary results. So we have our red contour is the relevant one, and the X is the best fit point. These might shift before publication, but physics. Once again, we're in our physics parameter space. We're drawing circles around where we think the true parameters might be. These are 90% confidence levels as well. All right, I will briefly talk about NSI here. IceCube has probed NSI effects several times. I've got links to papers there. The most recent analysis is Dragon NSI. It uses 3 years of deep core data, and it performed individual fits for the NSI parameters, by which I mean for each fit, it considered all NSI parameters 0 except for 1, and then it modified that and performed and minimized a test statistic. So that introduces a bit of model dependence because you're not testing situations where multiple NSI parameters are non-zero. Here are the contours. These are one-dimensional contours. Might take a little bit of imagining here. So this bluish color, cyan color, that is these wide bands are the Dragon results. And here we are comparing them against other results. So it's the kind of equivalent of this kind of graph, but in one dimension. These are once again 90% confidence levels. We're 90% sure the true value lies within the range that is highlighted. And so a more sensitive analysis has a smaller range. So you can see this is competitive with all these other experiments. So that is cool. But the idea is we can do better. And the current and ongoing analysis is osNext NSI. It uses 9.3 years of deep core data, so it's a significant statistics improvement. And also the idea is that hopefully the computational things will be worked out and we will be able to perform simultaneous fits for the NSI parameters. That relieves some model dependence, which is very cool to my mind. My upcoming work, I am joining the osNext NSI team. The current lead analyzer has graduated, and a few other people are coming in, including myself. My work on the FLERCNN analysis team has prepared me to continue contributing to analyses within the oscillations working group. And so next up for me then is working on osNext NSI, I claim. So I'll be continuing to learn NSI theory. I'll be collaborating with the outgoing analyzers to understand the analysis procedure. And I'll be collaborating with other incoming analyzers to further the analysis. And that's what I got.
Can you just say one word or two words about the training the program?
Sure. So I am currently inside the.
Not a question, it's a part of the factual information.
Sure. So other work that I will be doing besides NSI is I will be working on this train MI high energy physics detector instrumentation traineeship program. Kendall is my advisor for that, or my project advisor. I will be investigating the use of laser induced graphene. The resistive properties of that is what I will be testing. And I will be investigating its potential use in a field cage for a gamma ray TPC in space, which is a lot of cool words, I think. So right now what I'm doing is I am assembling a setup to produce laser-induced graphene and not burn people's eyes, and then measure the resistance of that laser-induced graphene.
I don't want the committee to be surprised when they're like out of the field, some other exciting stuff.
All right. Let's see. Okay. Let's first take questions from the audience.
And also Zoom people, feel free to raise your hand or type in chat or something, and I'll get to you. Lexi.
So with those, the recent analyses that you showed, this slide, instead of using deep core data, why specifically the deep core data?
So deep core is the, here, let me flip back to the deep core slide. Deep core has this tight instrumentation with respect to, or in comparison to the regular IceCube strings. And the tight instrumentation allows you to reconstruct lower energy events. And these lower energy events are the ones that we see in our oscillations, the oscillations pattern in.
Okay.
The reason why more dense instrumentation allows for reconstruction of lower energy events is that the deposited Trenkov light for lower energy events is over a smaller range and it's a smaller amount of light. So you want more sensitivity in there, more resolution, like literal pixels.
Thank you.
Questions? Anyone in Zoom? Thanks, Nick.
So, forgive me if we start out wasn't paying attention, but I understand how the scattering events inside like IceCube here matter significantly on determining the pattern. You showed this nice animation with sharing light and how you can reconstruct that.
Yep.
On an earlier plot, you had shown where like you have the red line and the blue line. I'm kind of curious about the atmospheric effects. So like scattering in the atmosphere. I don't know if that's like significant or what you're trying to measure though.
I know that. Right. I don't have numbers on this. I get the sense that because the neutrino path is so much more through the Earth than the atmospheric effects are small. I believe we model it though, because we model the atmospheric flux. So I believe we probably model other things going on in the atmosphere, but I don't have a solid answer on that. Liz.
So I think I'm having trouble separating what is like the NSI effects from the matter effects. So
Sure.
how would NSI effects affect that plot there?
Right.
What would
Okay.
the third line look like?
I can pull up. Oh, it's on the wrong computer. I can physically show you on my computer, but I don't have it in the backup slides. There are plots that you can make that show NSI parameters affecting these oscillations. And you can use those plots to see what is the relevant distances and energy ranges for the different NSI parameters. I should have that in the backup, and I do not.
Can you briefly define features? Like, is it that it's 10% down? Is it that there's really funky shapes in the middle? Like,
So since our parameterization is perturbation theory, for small differences, it'll look a lot like this. And as you increase that scale more and more, and the way that we have the scale set here is, where do I have it? When these parameters approach 1, that approaches the same effect as normal matter effects. So as you increase these parameters towards 1 or above 1, you get some pretty funky shapes, I would say. And that it's a little hard to visualize because we're in such a high dimensional space. For all the plots that I was looking at, they were all visualized for exactly one NSI parameter being non-zero. But there are all sorts of shapes you can make with multiple NSI parameters being non-zero. I should also mention they are the off-diagonal parameters are complex. They also have a phase, and that also influences the oscillations. This matrix is Hermitian, so the diagonal ones are real, the off-diagonals are complex, and the mirrored ones are related through complex conjugate. Mika?
I'm curious, you're oscillating the plots. How long did it take to plot this? Because it looks like your resolution between each of them is pretty nice.
So these aren't histograms or anything. These are just oscillation probabilities. So it's only math. You don't need it's only math. It's all only math, right? But these you can get in maybe like 3 lines of code through the analysis software, and it takes maybe 10 seconds to run.
That's after several years.
Yes. This is, I'm very much on the back end here, or the front end.
All right, any questions? Any other questions from the audience? And nothing online, I guess?
Anyone online have a question? I haven't seen anything in the chat. I see there's Joe here. I wonder who that Joe is, but no need to answer right now. Some Joe.
Okay, if there's no other questions, then I think we'll ask the audience to leave and we'll go into closed session, but thanks again for a good talk, Ben.
Thank you all for coming.
Thank you.